Hello everyone, I am Dr. Krishna Sarker, Department of Electrical Engineering. Here in this session, I will be going to discuss about root locus technique or root locus analysis. This is linear control systems, lecture series on linear control systems, lecture number 37. So our new topics, root locus analysis. What is root locus? Why root locus, advantage of root locus, and procedure of root locus. This is our target. So, root locus analysis. Root locus analysis is a graphical way for examining how two roots of a system change with variation of a certain system parameter, commonly a gain within a feedback systems. Another point, the root locus technique in control systems was first introduced in the year of 1948 by Evans. This is a technique used as stability criterion. This is a technique used as stability criterion in the field of classical control theory, which can determine stability of the system. And another point, the stability of a closed loop control system is determined from the location of the roots of a characteristic equation. For a system to be stable, the roots of the characteristic equation should be located in the left-hand side. So last point is the very important point. This is a technique. The stability of a closed loop control system is determined from the location of the roots of the characteristics equation. So first calculate roots of the characteristics equation and determine the stability of the system. For a system to be stable, the roots of its characteristics equation should located in right-hand side, left-hand side of the S-plane. And the next point, the root locus technique in control system, we will evaluate the position of the roots, their locus of movement and associated information. This information will be used to comment upon the system performance. The root locus plot the poles of the closed loop transfer function in the complex S-plane as a function of a gain parameter. So the root locus plot the poles of the closed loop transfer function in the complex S-plane as a function of the gain of the parameter. So this is the root locus first introduction part, and mainly negative feedback closed loop control systems. So what is negative feedback closed loop control systems? Suppose R of S reference input. This is also called excitation. This is also called excitation or reference input. And this is the always positive. And this is the comparator or summing point or error detector. And this signal actually error signal, E of S equals to error signal. Then G of S equals to process gain or control gain or system gain. And the output C of S is called controlled output or overall output. And this is the feedback path. H of S equals to feedback element. And the feedback gain equals to B of S. So this is the closed loop negative feedback control system because this feedback negative. And the overall transfer function, what is the overall transfer function already discussed? C of S by R of S equals to what? Hence, the above feedback system can be reduced to a single block diagram. So what is the input? R of S equals to input. And what is the overall system gain? GS by 1 plus G of S into H of S, and the overall controlled output C of S, and the output by input ratio is called the transfer function. Then the overall transfer function CS by RS equals to GS by 1 plus G of S into 1 plus G of S into H of S. This is the overall transfer function, and denominator terms 1 plus G of S H of S is called characteristics equation. 1 plus G of S H of S equals to 0 is called characteristics equation, this part. So this is for negative feedback transfer function, closed loop transfer function. When positive feedback, this does just this portion negative, just this is the negative. This is the negative value. So this is for negative positive feedback transfer function CS by RS equals to GS by 1 minus G of S H of S when positive feedback, when this is positive, when this is positive. Then concept of characteristics equation. What is the characteristics equation? For positive feedback system, positive feedback system, the transfer function CS by RS equals to what? GS by 1 minus G of S H of S. So the denominator terms 1 minus G of S H of S is equals to 0 is called characteristics equation of the system. So 1 minus G of S H of S is called the characteristic equation. This portion is called, this is the characteristics equation. That means denominator parts is called characteristics equation. Then for negative feedback system, already discussed, the transfer function CS by RS equals to GS by 1 plus G of S H of S. So what is the characteristics equation? And the characteristics equation 1 plus G of S H of S equals to 0. This is the characteristics equation. So this is the very important part from introduction. First calculate roots or poles or roots of the system. So calculate just roots from this equation 1 plus G of S H of S. This is the characteristics equation for negative feedback, and 1 minus G of S H of S equals to 0 is called characteristics equation for positive feedback control systems. So root locus plot, angle and magnitude condition. So what is the angle of magnitude condition? From characteristics equation 1 plus G of S H of S equals to 0. This is the characteristics equation. 1 plus forward path gain or forward gain and multiplication of forward gain and feedback gain is called the open loop transfer function. This is also called G of S H of S, also called open loop transfer function, and 1 plus G of S H of S is called characteristics equation. So this is the characteristics equation. Or from this equation, G of S H of S equals to what? This is equivalent to -1, just -1, or this is also G of S H of S equals to -1, and imaginary part what? Imaginary part J0. So -1 plus J0 point is called the critical point. This is also very important. This is also very important. -1 plus J0 point is also called critical point. And G of S H of S equals to what? So one angle of at an angle plus minus 180 degree. This is also called one at an angle plus minus 180 degree, plus minus 180 degree. And again, from this equation, G of S H of S equals to -1. So mod of G of S H of S equals to what? Mod of G of S H of S equals to 1. This is the magnitude of the system, the magnitude of the open loop system, or G of S H of S, magnitude of the. Then at an angle G of S H of S equals to what? This is equivalent to plus minus 2k plus 1 whole into 180 degree. This is the angle of the system, plus minus 2k plus 1 whole into 180 degree. Actually, -1 plus J0 point. This is the -1 plus J0 point. This -1 plus J0 point, -1 plus J0 point equals to 1 plus minus 180 degree. This is the formula. 1 at an angle plus minus 180 degree. Then -1 plus J0 is a point on a negative real axis, and it can be traced as magnitude 1 at an angle. What is that an angle? 180 degree, 540 degree, 900 degree, etc. So this is the actually angle and magnitude condition. This is the angle and this is the magnitude, and -1 plus j0 point is called critical point. So this is the very important for root locus plot, angle and magnitude condition. Then step number 2, what is the starting point? This is also very, very important part. What is the starting point and concept of the starting point? What is the definition? The root locus starts k equals to 0 from the open loop poles. The root locus starts k equals to 0 from the open loop poles. So what is the meaning of k equals to 0? Suppose 1 plus g of s, h of s equals to characteristics, equals to 0 is called characteristics equation. And the open loop transfer function g of s, h of s equivalent to k into suppose s plus 3 divided by s plus 5, where s is equal to -3, 1 0 position, and s is equals to -5, 1 poles position, and jd ROS zeros position. Then what is the characteristics equation? 1 plus g of s, h of s equals to 0, or 1 plus, put g of s, h of s value, k into what? S plus 3 divided by s plus 5 equals to 0. And this is equivalent to what? S plus 5 plus k into s plus 3. This is the main point. For starting points, root locus starts k equals to 0. K equals to 0. So put here k equals to 0, then this value 0, and we get s plus 5 equivalent to 0, or s equals to -5. This is the starting point, and s is equals to minus point means pole position. Pole position. If we consider this is the real axis, this is the imaginary axis, then the pole position, this is the pole, s is equal to -5. For what condition? At k equals to 0. When k equals to 0, the pole position equals to -5, and this is left hand side. This is left hand side. This is left hand side. S plane. So this is the definition of starting point. Root locus start at s is equal to -5 and k equals to 0. This is the conclusion, or this is the definition of the starting point. This is the definition of the starting point. So what is the ending point or terminating point? What is the terminating point or ending point? The root locus terminates k equals to infinity, either on open loop 0 or infinity. This is also VVI, or this is also very important definition. Root locus ending point. Suppose what is the transfer function? Our transfer function g of s, h of s equals to k into s plus 3. This is just example, s plus 5. Then characteristics equation 1 plus g of s, h of s equals to 0. Or 1 plus, put here g of s, h of s value, then we get s plus 5 equivalent to 0. This is equivalent to s plus 5 plus k into s plus 3 equivalent to 0. Then for terminating or for ending point, what is the condition? K equals to infinity. So put here K tends to infinity. Put here K tends to infinity. Infinity into something large value. Then S plus 5 negligible, because infinity into S plus 3. Then S plus 3 equals to 0 or S equals to minus 3. This is the zero position, JD, RO, zero position. So what is the pole zero construction? This is the pole zero construction. Real part, imaginary part, S is equals to minus 5, K equals to 0. This is the pole point, pole position, and S equals to minus 3, K equals to infinity. This is the zero position. So this is the zero position. That means all the poles and zeros left-hand side of the S-plane. Then open loop system stable. This is the left-hand side of the S-plane. Pole position S is equals to minus 5, K equals to 0, and zero position S equals to minus 3, K equals to infinity. So root locus starts K equals to 0 and terminate K tends to infinity. K tends to infinity or open loop 0. So this is the starting point. This is the starting point, and this is the terminating point. This is the terminating point. This is very important. So this is the ending point definition. Then, so the terminating point, that is K equals to infinity point on the root loci, are at zeros of the open loop transfer function. Open loop transfer function, zeros of the open loop transfer function. This is the ending points. Example, suppose G of S, H of S equals to Ks plus 3 by S plus 5. So what is the pole position? This is the real axis, this is imaginary axis. Then this is the pole position. S equals to minus 5, K equals to 0. And this is the zero position, S equals to minus 3, K equals to infinity. S equals to minus 3, K equals to infinity. So pole zero location and all the poles and zeros left hand side of the S-plane, then system will be stable, open loop system stable. This is the pole zero location, and root locus starts open loop poles. That means S equals to minus 5, K equals to 0 point, and terminate S equals to minus 3, K equals to infinity. This is the terminating point. This is the starting point. Then step number 4, number of branches. This is also very important point. Number of branches, root loci. The number of branches of the root locus are n equals to p if p greater than z. P equals to what? Number of poles, and z equals to what? Number of zeros. N equals to p. That means number of branches equals to number of poles if p greater than z. If number of poles greater than number of zeros, then number of branches equals to number of poles. Similarly, if number of branches equals to number of zeros, if number of zeros greater than number of poles, So the number of root loci is equal to the number of poles or zeros. That means if p greater than z, then number of branches greater than equals to number of poles. If z greater than p, then number of branches equals to number of zeros, where p is the number of finite poles of GSHS. However, in control system, the number of poles of G of S, H of S must be at least equal or greater than that of zeros. That means in normal case, p greater than 0 or p equals to z. That means normal case, poles number always greater than zeros number, or poles equals to zeros. This is the normal case. Usually p greater than 0. Therefore, n equals to p. Therefore, n equals to p. This is the number of branches. Definition of the number of branches. Then intersection point of asymptotes on real axis. This is also very important for root locus construction, design of root locus construction. The asymptotes intersects at point on the real axis sigma. Sigma on the real axis is given by sigma equals to summation of poles minus summation of zeros divided by poles minus zeros. This is also called summation of poles minus summation of zeros divided by p minus z, or finite summation of finite poles of GSHS minus summation of finite zeros of G of S H of S divided by number of finite poles of GSHS minus number of finite zeros of GSHS. This is the intersection point of asymptotes on the real axis, sigma. So intersection point calculation, definition, summation of poles minus summation of zeros by p minus z. Or another definition, step number 6, the angle of asymptotes of the root locus. The angle of asymptotes of the root loci s equals to infinity. Behavior of the root loci at s equals to infinity. This is also very important definition. When p not equals to z, that means number of poles not equals to number of zeros, there will be p minus z. That means poles minus zeros number of root loci that approach infinity in the S plane, as p minus z number of root loci will terminate at 0 at infinity. So this is also very important definition. The higher value of k is large, the root locus branches are approximated by asymptotic to straight line on angle with the real axis given by, what is the definition? This is the definition, theta k equals to 2k plus 1 whole into 180 degree by p minus z, where k equals to 0, 1, 2 up to p minus z minus 1. So what is the angle of asymptotes? Angle of asymptotes theta k equals to 2k plus 1 whole into 180 degree by p minus z, where k equals to 0, 1, 2 up to p minus z minus 1. This is the angle of asymptotes definition. Then step number 7, intersection point of root locus with imaginary axis. This is also very, very important definition. The value of k and the point at which the root loci intersects the imaginary axis of S plane may be determined by applying Routh-Harris criterion, the root locus of the intersection point of the imaginary axis. That means, what is the imaginary intersection point? Just calculate Routh table and determine the imaginary intersection point. So this is also very important for imaginary intersection point calculation. Then another point, step number 8, angle of departure from poles and angle of arrival for zeros. So of the root locus. So angle of departure from poles and angle of arrival at zeros of root locus. That means angle of departure from poles and angle of arrival at zeros of the root locus. The angle of departure from the pole -1 plus j1 is calculated below. Suppose this is on also example. This is the real axis. This is the imaginary axis. And suppose one pole at s is equal to 0, k equals to 0, and another pole s is equal to -5, k equals to 0, and another pole s is equal to -6, k equals to 0, and one imaginary pole s is equal to -1 plus j1. This is the calculated point, the angle of departure from this point, and the conjugate value -1 minus j0 and k equals to 0. Calculate from this point the angle of asymptotes, angle of departure. What is the angle of departure? And this is another 0 point. This is another 0 point. Suppose s is equal to -3, k equals to infinity. This is another 0. So calculate angle of departure with respect to -1 plus say 1 point or k equals to 0 at that point. So connect from this point to this point projection, draw one, and another projection, draw s equals to -1 to z2 k, s equals to -5, k equals to 0, another projection. This is the projection line 1, 2, 3, 4, 1, 2, 3, 4, 5. And what is the angle of departure? Another draw here, parallel to x-axis or parallel to real axis, then calculate angle of departure from this pole or this pole. So what is the angle of departure? This is the angle of departure phi 1 or phi p1, and this is the another angle for poles phi p2, and this is for phi p3. This is for phi p3, and this angle for this pole phi p4. For 4 pole phi p1, phi p2, phi p3, and phi p4. And for this 0, the angle phi z1. So this is the angle of departure calculation process, the angle of departure calculation process with respect to imaginary poles. Then step number 9, existence of the root loci on the real axis. Existence of the root locus on the real axis. Any point on the real axis is a part of the root locus if and only if the number of finite poles and zeros of GSHS on the real axis to the right of the point is odd. This is a very, very important part. Any point on the real axis is a part of the root locus if and only if the number of finite poles and zeros of GSHS on the real axis to the right of the point is odd. The existence of the root loci on the real axis is shown in figure. It is apparent that the occurrence of the loci on real axis is not affected by the complex pole and zeros of GSHS. So this is the example of the existence of the root loci on the real axis. Suppose this is real axis, this is the imaginary axis. Again, this is the s is equals to 0, k equals to 0 point, and another pole s equals to -5, k equals to 0. Third pole s is equals to -6, k equals to 0. And this is the 0 position, s equals to -3, k equals to infinity. So calculate existence of the root locus on the real axis. Suppose this is the point. This is one point, s equals to a. Sorry, this is the point, a point. A point. For with respect to this point, a point, calculate in between s equals to 0 and s equals to -3, root locus exists or not. This is our target. So what is our target? This is our target. This is our target. This is the point A. This is the point A. And this is the right-hand side, and this portion left-hand side. What is the definition? Summation of poles plus summation of zeros equals to odd. Suppose in this case, right-hand side summation of poles plus zeros equals to just 1. Just poles equals to 1 plus 0 equals to 0. Then this is equals to 1. That means odd. Root locus exists in between s is equal to 0 to s is equal to -3. Root locus exists. Root locus exists. This is the definition. So another condition. So this is the odd number, so root locus exists. Another point, in between s equals to -3 to -5, in between s equals to -3 to -5, one point B. That means -3 to -5 root locus exists or not. This is our target. B, summation of poles plus zeros again equals to even. Why even? Suppose draw one projection. And this is right-hand side, right-hand side, right-hand side summation of poles equals to 1 and summation of zeros, this is the 0 plus 1 equals to 2. This is even. That's why root locus does not exist. This point, root locus does not exist. This is the dotted line. This is the dotted line. Again, suppose another point in between s equals to -5 to -6, C point, root locus exists or not? The summation of poles plus zeros equals to odd. That means root locus exists in between s is equals to -5 to -6. Why? Again, draw one projection line from this point. This point, this is the right hand side, this portion right hand side, and summation of poles. This is one pole, this is one pole. That means 2 pole plus 1 0. This is 1 0 3. That means odd. Root locus exists in between s is equal to -5 to -6. Root locus exists. Similarly, for this point, this is the D point. Summation of poles equals to 1 2 3, and the summation of zeros equals to 1. Root locus does not exist. In s equals to -6 to -infinity. S equals to -6 to -infinity. Root locus does not exist. This is the existence of the root locus on the real axis definition. This is the D point. Summation of poles equals to 1 2 3. So put here poles equals to 3 and zeros equals to 1 just, and equals to 4. That's why root locus does not exist. The root locus does not exist. Then step number 4, breakaway point. What is the breakaway point? The breakaway point is dk ds equals to 0. dk ds equals to 0, and the point lies between the two open loop poles of G of S, H of S. This is the breakaway point definition. So what is the process? What is the process? Suppose this is our open loop transfer function, G of S, H of S equals to k into S plus 3 divided by S plus 5, and the characteristics equation 1 plus G of S, H of S equals to 0. Then put here k into S plus 3 divided by S plus 5 equivalent to 0, and this is equals to k into S plus 3 divided by S plus 5 equals to -1. Then this is equivalent to k into S plus 3 equals to minus S plus 5, or k equals to minus S plus 5 divided by S plus 3. Calculate dk ds, and this is equivalent to 0, and calculate the S value. This is the breakaway point in between two poles. Breakaway point. Suppose this is pole number 1 and this is pole 2. And this is the breakaway point. Breakaway point. So this is the procedure for calculation of breakaway point. Then symmetry of root loci. The root loci are symmetrical about the real axis of S plane. The proof of self-evident, since for real coefficients, the roots of the characteristics equation must be real or in complex conjugate pair. So in order to draw the root loci, only positive value of omega need to be considered, because the real part of z omega is even and the imaginary part is odd. It follows that imaginary of z minus z omega is z omega equals to minus imaginary of z omega is z omega. But real of z omega H omega minus equals to real of Z omega H omega. So symmetry of the root locus or the locus or root loci are symmetrical about the real axis of the S plane. So this is also very important. This is also very important. The root locus for negative value of omega can be made by reflecting the root loci for positive frequency upon the real axis of the S plane. So symmetrical of the root loci. Advantage of the root locus technique. What is the advantage of the root locus technique? In control system, root locus technique is easy to implement as compared to others method. That means Nyquist, M-circle, N-circle, Bode plot. This is the very easy technique or easiest technique. We can easily expect the performance of the whole system with the help of root locus. Root locus technique provide the better way to indicate the parameters. So this is the advantage of the root locus method. Thank you.